All right, might as well get going. Welcome back to day 2 of data structures. I'm still Chris Craig, and we are back for round 2. Here is what we're going to talk about today. First of all, on the anonymous feedback, might as well cover that right now. I received a couple pieces of anonymous feedback, so thank you to those who sent those. One person I couldn't reply to just because you hadn't signed up for the system in order to get a reply back, but needless to say, I did receive your feedback, so thank you very much. Anybody else who wants to do the anonymous feedback, feel free. So we can do that. The other person asked about when the midterm was. The midterm, I kind of screwed up the syllabus, both with the midterm thing and also with the tokens. I don't think we're going to actually have the token thing. If you have an issue with not getting homeworks in on time, like you have to have an extension, email me and we'll discuss it. It's not the biggest deal in the world, but I figured that was probably easier than doing the whole token thing. But I'm up for discussing it if you do have comments on that. The midterm is before spring break, so it's going to be the Wednesday before spring break. So if you are going out on spring break and don't want to think about computer science or data structures, that's fine. Okay. All right. I'm going to talk about this thing called the WeCode conference. Then I'm going to do a little UNIX tip of the day. So I know a bunch of you have never used UNIX before, and I figure if we do a little bit of UNIX every day, kind of things that will make your life easier, that'll help when you're actually going to compile your programs and look at your programs and so forth. And then I promised the other day I'd show you something from the obfuscated C programming course, what is it? I don't know why I'm blanking on the name. But anyway, the obfuscated C is online, and I'll show you some things from that, and it's kind of fun. And then finally, we'll talk about homework 1, which technically is actually due tonight. I think I said it was due last night, but I think the provide will still accept it up until tonight. So if you haven't quite finished that yet, for whatever reason, you can still do that. And then we'll get into the kind of the meat of the lecture, which is dynamic arrays, which I think a lot of you have seen before, but we'll do a little refresher on it and see what we can figure out about that. OK, questions before I begin? All right. So for the women in the class, there's this Women Engineers Code Conference coming up in February, and it's down at Harvard. And the women in CS at Harvard actually put it together every year, and it's kind of cool. So if you're a CS major, you probably got an email with this already. But if you didn't, here's the details. It's going to be speakers. There's going to be workshops and lightning talks, and a little bit of there's a recruitment boot camp there. So if you're looking for a job in the summer or kind of longer term, great thing to go to. So there's the information. I'll probably put this back up on the screen next week sometime to remind everybody again. But feel free to sign up for that, and it sounds like it's a lot of fun. OK. The next thing I want to quickly talk about, a couple of UNIX tips. OK, most of you guys at this point have probably seen some of these, but I want to show you a little bit more about what some of them do, and then I'll use them during the rest of the class too, so you'll kind of get a feel for what those are as well. OK, let's see. Hopefully I got this set up right. Nope. How about this way? There we go. All right. So if you have your window up, all right, first things first UNIX tip. If you want to actually clear your screen, just type clear. Pretty simple. Or reset also does that. And you get a nice clean screen there. The ls command. Many of you guys have actually used it already. The ls command gives you a list of your folders. In fact, let me go to some folder where I've got some more stuff in my main. Let's see. How about the main folder? There we go. There's a bunch of files in my directory, right? Well, that doesn't necessarily give you the most information you can get about that. And there's lots and lots of flags that you can use with UNIX with the ls command to actually get more information. So for instance, the -al, it's two flags in one actually, -al stands for all files, and then a list of files kind of with extra information. Okay? So ls-al will give you all the files being the hidden ones as well. And in the UNIX file system, files that begin with a period are actually hidden. OK, so there you go. There's all my files right there. Okay, and this is extra information. This column here gives you information that's, if it's D, it means it's a directory. These little permissions here tell you who gets to look at your files or change them. The first three are you. The second three are your group. And if you'll notice over here, I happen to be part of the faculty group, while my files happen to be part of the faculty group. And then there's everybody else in the file system. Like you guys could actually go and read some of these files from my folder, my directory, if you wanted to. Okay, you probably won't have to worry about that, but it just stands for read, write, and execute, if it happens to be like an executable file. OK, don't worry about the next column. It's silly. The other column tells us who the file belongs to. That's me in this case, and then what group it's in. The next column gives you the actual size of the file, which is kind of nice. And then finally, probably the most important one is when the file was modified last. And make actually uses that information to decide whether it needs to recompile your files or not. And then finally, the file name over here. OK? The command that I like, the flag that I use a lot these days, ALRT. The R stands for reverse, and reverse the order. And T stands for sort by time. So what this does is it actually orders your files from the top one is the oldest down all the way to the bottom, which is the newest file, the last one that you actually modified. So that's nice if you want to see what files you've just recently modified. This happens to be the list of the commands that I've typed recently. But all the other things I must have modified at some point or another. OK, so that is the ls command. You'll use that a lot. OK, let's go to, let's see another one. Data structures, day 2 heights, maybe. OK, we'll look at this a little bit later. Another command called the cat command, C-A-T, which stands for concatenate, meaning to put two things together, actually can be used to put files together, but also to print things out on the screen and just list your file out to the screen. So if you type cat, and then let's look at this file heights.h. OK, what it does is it just prints it all out, straight out, the whole thing, which can be useful and might not be too useful if it's like a longer file than more than a few lines. So there's another command called, well, there's two commands. One's called less and one's called more. More was before less, but they're basically the same thing. I like less because it gives you some extra things. But if you type less and then the name of the file, let's do the same file there, OK, it will actually give you chunks of the file such that you can use the arrow keys to go down and back up and look at the file and scan through the file. So it's kind of nice that it will allow you to do that and see the file kind of in chunks at a time. And if you hit the space, it gives you a whole another page. OK? And then Q quits out of that. And it actually brings you back to wherever you were. So it lists it and then throws the original screen back up there. OK, so a couple little tools you might use. And we'll see a couple others as we go along during the rest of the day. Oops. OK, questions on the UNIX tools? No. Awesome. All right. So let's see, what else did I say I was going to do? The obfuscated C. OK, so I showed this to the class earlier, and some people didn't quite get what was going on here. See this thing that says fluid right there? That's actually a program. OK? It's actually a program. You can kind of tell. You can kind of tell it's a program because right at the top you can see the include, and you can see some of these other things. And then it just gets to be like garbage. Right? It looks like garbage anyway. But that's actually a program. And in fact, this is the whole program that the guy who submitted this to the contest, this obfuscated C contest that happens every year or two, actually submitted. Now, you can see it says fluid, right? So maybe that gives you an idea of what might actually happen when it does this. But you can grab this program off the internet and then compile it on your computer and run it. Somebody was nice enough to do that for us already. And let's see if I can actually, hang on, it's on the wrong screen here. Let's see. How about, maybe not, hang on. Let's see, let's do this and then this. And there we go. OK, so somebody was nice enough to, let me put the screen down a little bit, to compile this for us and show it. So this is that's the program. When you list out the program, that's the program. It looks like garbage, but it says fluid, whatever. Right? And the person's going to actually play this. Unfortunately, it's got sound, but I'll play it up. I couldn't get the speakers to work. But you will see what it does. after I've hit play. So what's going to happen is they're going to compile it, and then they're going to take the program itself and feed it into the actual program as it's running. Like the text of the program is going to get fed into the program. Watch what happens. Oh, there you go. Bunch of compile stuff. OK, compile it, and then they're going to feed it in to itself. These are like text characters. This is not graphics, right? Those are like slashes and hashes and periods and things, right? And that was the whole program. That like program that fit on the screen was it. Okay. You can also come up with other ones. So this is another program, another text file that he's feeding into the program. All right. And it just goes on and on. You can get all sorts of these things. Anything you want will be fed into that. The guy obviously knew a little bit about physics. Right? This one's a fun one. Whee. Now, I don't think you would have known that it was going to do this when you looked at the program. That was kind of the point. Let's show you one more. And you can make your own file and feed it in here, and it'll just do this, just based on a couple rules. Let's see. OK, so here's the last one I'll show you here. He's using less, by the way. OK, this one is color. All of a sudden, it just adds color to it. 5 extra lines of code, right? So anyway, that's the obfuscated C. That's one of the winners from this year. Bruce actually showed me one. Let's see, where did it go here? Bruce showed me one as well that I actually compiled for my computer. It looks like this. So, and this is kind of I like this one because this is the program right here, right? It's garbage, right? You can't even see anything, right? But what it looks like a little flag. These flags are called signal flags, semaphore flags, and they're used in the Navy and on shipping for ships to communicate with each other by like using these flag symbols. So you don't have to have a radio. So if it's like, you don't want to be on the radio or whatever, they don't use them so much anymore. They still teach them how to do it. But if you want to do an A, like you have your 2 flags down like this, and a B is like this, and whatever. And this guy wrote a little program that looks like this. And let's see if I can actually show it to you. Where'd it go here? There it is. OK, let's see. Obfuscated C. So let's do this. Let's echo, or I'll do it up here, echo data structures. And what we'll do is this is a little pipe command, which means you send this information into the file, into the program. I think it's Anderson. There we go. And out comes this. See the little guy there? He's holding up a flag down there, a flag up here, and a flag down there. And then this is his head, and right, flag down there. And then when he gets to a space, he just puts 2 flags down there. Yeah. So that program that looked like a flag puts out, the letters in semaphore. The best part about this was this won the category in the contest for best use of flags, which I thought was kind of funny. OK. So anyway, I should not have to say it, but please don't make your code look like this, right? We will not be able to grade it. The auto grader will fail miserably, and you won't be happy, and neither will we. But if you want to, start, learning this stuff so that you can enter this contest, by all means, right? You can certainly do that. OK. Any questions on obfuscated C? No? OK. Let's talk a little bit about homework 1, which, as I said, is actually not due until a little bit later. Tonight, rather. There were a couple things that we threw in there that I didn't necessarily expect you to either understand or do correctly, but I threw them in there just to kind of see what you would do. One of them was this idea of assertions, okay? And a number of people on Piazza asked questions like, what is this whole assertion business? And here's what it is, okay? We've talked about it on Piazza a bunch of times, but here's what's going on. When you're in your methods that you use, okay, for certain methods, we like to say that the method only allows certain input. And in this case, for rectangles can only have positive lengths and widths, right? So we said, all right, let's assert that the width has to be greater than 0 and the height has to be greater than 0. Now, the math works out either way. I mean, you can input negative lengths and out will come on negative perimeters, right? But it doesn't mean anything. So we're just kind of testing this. And what we said was like that the width and height had to be greater than 0. You want to do error checking like that in a way that doesn't, you don't want to, let me put it this way. You don't want to do program input and output like with the user in your method that is for a rectangle. If you're going to do input output for the user, leave that up to your tester program or the program that the program that actually runs these commands. You don't want to put error checking like input output into you don't want to, in your method that's for rectangle, you don't want to say, C out, I'm sorry, you put a negative value, right? And then please enter another value. You don't want to put that in the method. You want to put that kind of in a different part of your program so that it keeps those things separate. But in your method, you can say, if for some reason a negative value makes it in, let's crash gracefully. Okay? And that's what the assert will do. So if you include assert, or I think maybe assert.h or something like that as well, and you say assert, if you go and say assert, let's say width is greater than 0, right? What happens is when the program gets to that line, it actually checks. It says, if width is greater than 0, go to the next line. If width is not greater than 0, or less than or equal to 0, then print out this error message that actually means something and stop the program, like halt the program. Okay? And we mainly use it for debugging. Okay? We don't use it for, we generally don't use it for like production code, but for debugging it makes a lot of sense to use that. Okay? So let me show you if I can do this again. Let's see. Whoops. There we go. All right. I actually wrote a quick little program, I mean a really little program, that does this. Assertion, there we go. OK, so this is what it looks like. Less assert example.cpp. OK, that's it actually. This is the whole file, right? What it does is it says, make an integer that's equal to 0. Make another integer that's equal to 10. Assert that a is less than b. Well, a is less than b, so the program's going to get to here and go, no problem. Then it's going to assert that b is less than a, and it's going to say, I don't think so. Right? So let's see what happens when we run it. There we go. Now, notice what this printed out. Okay, this is actually your program. It has no real knowledge of your code, except that it's been encoded into the program itself, that on line 9 in your CPP file, in your main function, the assertion that b is less than a failed. That actually tells you something about it. So you can go back, when you see these assertion failures, you can go back and say, oh, what happened here? Why did that assertion fail in my program? Okay, so you know where it failed, and it tells you a little bit about it. Somebody on Piazza said, can't I just print out, whenever there's an error like that, just print out error? Sure you can. That doesn't tell you much, right? That doesn't tell you much. Yeah? You can use assertions wherever you want. You can use assertions in your main function or any of your other class functions or anything. Anywhere you want. You do have to make sure that the include assert is in that file. And assert.h is the same. Assert.h is the same, I believe. Yeah. Question?
Do you want us to remove all our assertion statements before we turn in a finished program, or are they fine?
Nope. You can leave the assertion statements right in the program. In some, again, we may test to see that your assertions come out. And what should happen is it should crash. So we had a little bit of trouble with the auto grader making it so that it didn't look like your program was wrong. Like sometimes it would say, hey, you crashed when it was supposed to, which is fine. But but leave them in. Yeah, sure. Other questions? Yes?
So for this first homework, if we had error statements, we didn't use assert, should we go back and
No, don't change it. Unless the question was, do we change it if we've already submitted it? Don't go back and change it. If for some reason it failed because you had the error statement in some way that it made the program not understand what was going on, then you could change it. But we will not take points off if you put that kind of error checking. Yes.
If you didn't have an error check at all, would you recommend that you go back and change?
Nope, don't worry about it. If you don't have to rechange it. No, at this point, I mean, the reason we put these, you will not get points off. If for some reason you do, let us know. We'll fix it. But if you didn't put those in, that was just to kind of see what you'd do with it. So no worries. Other questions on that? Yeah.
Follow up. So when you said you put those in, with the idea, did you have an implementation in mind? Did you have an idea that we would include them in when we were defining our member functions, or did you think that we would use it in the implementation?
It didn't really bother me either way, which I didn't have a specific way that I thought you'd do it. I just wondered what you guys would do with it. So, and now from now on, you'll hopefully know what's going on with that. One sec. Yeah.
Moving forward, should we always assume that we would check for valid input?
Well, in your program in general, you should check for valid input. Now, that's not really feasible in all cases because, it's hard to do. But, production code always has to do that sort of thing. I mean, the last thing you want is your program to fail. And you have to do your own error checking. But don't go overboard with it by all means. However, if we say in there, assert that this is true, then put it in there. Yeah. Yeah.
So can we kind of think of this as an abbreviated conditional section?
It really is. I mean, it is an abbreviated conditional. Although, I mean, it's more than that. It actually gives you a nice error message, and it's a way for you to do debugging, which is helpful. Yeah. So again, you wouldn't really use it too much in production code that you'd do for you'd take them out beforehand. That's it. Yeah.
Can you assert a data type?
You can assert anything that turns out that will produce a Boolean value. In other words, anything that you can compare, you can put in this assert. Assert is basically looking for a Boolean value, and if it's false, it does one thing. If it's true, it does the other. That's it. Okay. Anything else? All right. So that was assert. Okay, and again, I didn't expect you to put this in. We just thought we'd throw it in there to see what you guys did with it. The other one that I didn't expect you to necessarily handle correctly, and I'm going to spend a few minutes talking about this, is floating point comparisons. And we threw this thing called epsilon in the .h file, and a lot of people asked, like, what is this epsilon business? What's going on? Well, here's what the deal with that is. Okay, when you are dealing with floating point numbers, you have to be a little bit careful. Who here has heard before that you are not allowed to compare floating point numbers using equals equals? Raise your hand if you've heard that before. OK, only a couple people. Good. Well, after today, you will all have heard this. OK, here's the thing. So let's say we have a rectangle, right? Well, let's make it a square. At least visually, we'll make it a square, more or less. OK. If I have two numbers that are integers, okay, the computer has to store that information somewhere. The computer has to store that integer in somewhere in memory, right? And it might store a 3 there and another 3 there, okay? And this is going to delve a little bit into computer architecture, but not too much. Okay, the computer has to store that number 3 somewhere. And the computer generally has a range of numbers that it's going to allow. You've heard that your computers these days are generally 64 bits or 32-bit computers. If you've got a 32-bit integer, which is pretty common, that means that there's 2 to the 32, right, which is about 4 billion combinations of integers that will be representable. 0 to 4 billion or negative 2 billion to 2 billion. And you'll get 4 billion different combinations, OK? Well, question, how many integers are there from 0 to 4 billion? 4 billion, right? So what's nice is any integer you can think of between 0 and 4 billion, the computer will put that in memory and be able to return it to you as the exact number that you put in there. OK. The problem is when you start dealing with things like floats, 3.1 and 3.1, now we've got a different ballgame. OK? 3.1 and 3.1. Well, the computer has to store that. And a computer, as humans, we can look at that and go, OK, that's 3.1. And we know how to, we will know what decimal means and all that. the computer has to actually store that. It becomes much more tangible for a computer. It has to say, how do I represent 3.1? OK. From 0 to 2 to the 32, we said there's about 4 billion integers. How many floating point values? In other words, how many fractions are there or decimal values are there between 0 and 4 billion? Infinite, right? There's an infinite number. So there's no way, by definition, that the computer can absolutely store every single value that you give it. Like it can't actually do that. There's no way to store every value. It's only got a finite number of values that it can store. Because when it goes back and looks, it's got 4 billion to choose from. And the one you chose might not be one of those 4 billion, OK, as it turns out. All right, so what does that actually mean? It means that sometimes when you put a number in here, well, the computer has to make it one of those 4 billion that actually can be represented. OK, so it might not exactly be what you, as humans, think it is, but it's close enough in most cases. OK, it's close enough in most cases. Let me show you an example. Let me show you an example of this in, let's see, yep, wrong way again. There we go. OK, I like to use the Python language. OK, Python's nice because you can just open up a window and start typing commands, and it comes out. If I type a equals 0.1, you all know what that means. That means a is 1.1. If I type b equals 0.2, and then c equals 0.3, OK, we know what all those mean. If I was to say, and this is just like C syntax or C++ syntax, a plus b equals c, what do we expect? We expect it to be true, right? Because 1.1 plus 0.2 equals 0.3. And if I hit return, the programming language says that's false. OK? Well, here's how a is actually represented in Python. Or rather, 0.1 is represented. 0.1, 0, 0, 0, 0, and then a little 1 out there. Because 0.1 is not representable in the binary format that the computer knows. It gets close, right? But that's as good as it's going to do. All right? And b looks like this, 0.20001. Right? Anyone want to guess what c is? How about 0.2999999? Right? So it's going to be relatively close when you do the additions here, but it's not going to be perfect. Right? It's not going to be perfect. So when you try to compare those, if you just type 0.3, right, you'll get this value, 0.29999. If you just type point a plus b, you'll get 0.300004. Right? Because that's the nearest one that it can represent. So what you think, the way you got to that value is different, and therefore it might not be exactly what you think it should be. And therefore, when you try to do a, or in our case for the program, w equals h, or whatever, it may not come out right. OK. So what do you do about that? Right? All is not lost. OK? You can actually do something that's better than trying to compare them, because that may not work, and in fact won't work many times. But what you can do is you can use what we just put in a little variable called, we defined this value called epsilon to be like 0.00001. Using that, how might we tell if two numbers are equal to each other? Yeah?
So if you take the difference of the two numbers, you put the greater number first and then the smaller number second.
Yep.
Since they're not going to be exactly equal, we're going to expect some very marginal difference between the two. But if that marginal difference is going to be less than our epsilon value, then they're roughly close.
There you go. Long story short, subtract the two values, take the absolute value, and then compare to our epsilon. See what it is. That's very good. What's going on is you're just subtracting the two numbers. And by the way, if you're trying to tell, if you in real life, if you're taking two numbers and you're saying, are they equal to each other? Well, kind of in the back of your brain, you're really subtracting them. Or you're adding them up and you're comparing them somehow. A computer compares generally by subtraction. And that's not a bad way to do it. Where did the 0.0001 come from? I just picked it. I mean, I just said, well, if two numbers are closer than that to each other, then we're going to call it a square. You could pick any other value that you want. OK? So that's why you can't use this equals equals business when you're trying to compare floating point numbers. OK? Any questions on that? Again, if you didn't do that for your homework assignment, no worries. There's only one test we used that would have come up with this, and it prints out that you didn't do it, but that's because we were going to talk about it in class today. Okay, no points are going to be taken off for that. But from now on, you'll know that you can't compare floating point numbers. Okay? Yes?
So we're going to compare numbers with, why wouldn't we be using doubles instead of?
Good question. Why wouldn't we be using doubles than floats? Doubles have the exact same problem. There are just more choices. You've got 2 to the 64 choices or whatever. Well, actually, as it turns out, doubles and floats are the same in C++, as it turns out. But in most versions. But if you use like I think it's called a long or a long double or something like that, you can get more precision, but not perfect. You're still never going to get. You're still going to have the same issues. So yeah. Floating point values in general. Yes.
So we do that we can't compare floats period, or we can't compare them without having them.
Well, this is how you're going to compare them. So if you want to compare two numbers, you have to figure out a way to do it so that those errors that we saw don't come into play. And one of the ways to do that is using something like an epsilon, where you're subtracting and comparing to that value.
Oh, so you would manually compare them, like subtract
Yes.
them and compare. Okay.
You'd manually do. Oh, and to go back to the question before, the way we would do this in our program here is we would use we could do if w minus h, right? If w minus h is less than epsilon, we could use that. But the problem is that's not the absolute value. If this happens to be the smaller number, then it's always going to be less than epsilon. So what we want to do is find the absolute value. The way you find the absolute value is use the absolute value function, which is built into the language. I think you need to do something like include, I think it's C math works. Math.h might work as well. There's a couple different ways to get the math library. And then you use the floating point absolute value function, like that, and that will give you the absolute value of those two numbers. Or you can just write your own absolute value function. It's pretty easy to write. Yes?
What would you do if you were comparing two floats and trying to see which one is greater than the other? Like if you took the A and B that you had before, 0.1 and 0.2,
Yeah.
if you add them together, you get 0.3004.
Sure.
And you wanted to compare it to something like 0.300001.
Good question.
How would you compare it that way? Because clearly the C that you're given is actually smaller, is actually larger than what A plus B should be.
Yeah, that's a good point. This epsilon business is not a catch-all for everything. You would have to either make a smaller epsilon if you were to try to compare numbers like that. Now, doing less than for two floating points is actually reasonable. Okay, less than works, or less than or equal to, I guess, works. But equals doesn't work because there's only one value that means equals, right? Less than or equal, there's kind of a range. I mean, there's lots less, or equal. So you can use that.
Right, but in that specific case, A plus B would appear to be larger than C when it's not.
Well, yes. I mean, and that's one of those corner cases, and it's a case where nothing you can really do about it, just because of the way that the computer stores numbers. Yeah. Good question, so. Anybody else? Okay. All right. So that was your homework. We will try to have the homework graded by the end of the weekend, let's say. We're going to try to turn these things around pretty quickly. Okay. All right. Uh-oh. What happened there? That's weird. Hang on. I don't know what happened there. All right. What this is supposed to say is dynamic arrays will actually start with regular old arrays and move into dynamic arrays. So we're going to move into dynamic arrays. You have seen dynamic arrays in Comp 11, I hope. Yes? So a few people have anyway? OK. We'll refresh you here. For those of you who haven't, that's OK. Hopefully we'll get you up to speed on this quickly. But first, what we need to do is talk about these things called arrays. And I actually wrote a little program to look at these. OK. It is called heights. And what I'm trying to do is I want to find the average heights of celebrities, as you do. Right? It turns out that if you look up celebrity heights on the internet, you'll end up with this web page. It's like celebrityheights.com or something like that. And it's like 6,000 different celebrities and like how tall they are. Right? And I want to figure out the average because I think that's an important statistic in a first world country. the average of the heights of your celebrities, right? So I decided to write a little program to do that. OK, and here's the program. What I'm going to do is kind of go through the program. It's going to look very much like your rectangle program in kind of the broad scheme. So let's see. Let's use less, and let's do heights.h. I wrote an h file. And let me talk about this. I'm going to show you a couple of C++ things that you may not have seen before that are going to be important kind of later on. And if you read a lot of C++ code, you will see this very often. So you might as well get used to it now. There's this command. So the first thing I have is this thing called typedef. Okay, T-Y-P-E-D-E-F. And it's a keyword in C++. And it means just what it sounds like. It's a type definition. Okay? And what you do is you say typedef, and then you put some type that you know, like for instance int, right? And then you write some other word. So we could pick I don't know, Billy, right? Right? And what this means is the compiler will say, anytime I see the word Billy in your program, I'm going to know that that means an integer. Okay? And then you say, well, why do we even bother doing that? Why don't we just write int? It's actually shorter, and it means int, right? Well, the reason is because, so everywhere in my program, I put Billy everywhere. And then later, I say, you know what? I want what I referred to as Billy to not be an integer anymore. I want it to be a float, right? So what the program does is you go and you change it once in your header file to a float, and then everywhere else it's now a float. Okay, so it makes it easier to do changes to your program that are significant all at once. Okay, in this case, I didn't use something fun like Billy. I used value type, which is going to stand for the type of value that I'm going to put in this array that we're going to create. OK, remember from the other day, an array is a piece of memory that has spots in it where you can put values. OK, that's all an array is. OK, don't worry about all that other verbiage up there. We'll get to that at some other point. What else do I have in here? I say static const size t capacity. You may not have seen any of these words in C++ before. This part simply means, it means a couple of things, but the bottom line for static const is you can't touch the value of this variable. Once you set it, you don't set it again. You can't change it. You can't do anything with it. If you try to, the compiler will complain and give you an error. And so you can't change static items or const items. Static means that's for the program itself you're using. Don't stress about the details of that. Size t is actually another type def. Okay, size t is a type def that stands basically for an integer, but it depends on the computer system you're on. Okay, and they do this so that C++ programs can be what we call portable, meaning that in one computer that's like 8-bit computer, size t might be 8 bits long, and in another computer is 32, it'll be 32 bits long. And what the size underscore t means is that it will allow you to reference any position in any array that you can get. So if you get an array that's as big as the computer you're on allows, you will be able to reference that last value using a size t variable. In other words, it's got enough, it's a big enough variable type that it allows you to reference anywhere that you want. So don't worry about the details of that. You could put int and it would work fine for this program. But again, if you read lots of C++ code, you will see size t all over the place. You might as well kind of get used to seeing it now. OK, so of course I'm going to have a constructor for my class. OK, it's just going to be one default constructor, very easy. And then I'm going to have some modification members. In other words, I'm going to have some member functions that are going to do something to this array. I'm going to have three in particular, only one of which I'm actually going to use this afternoon. The first is called append. And that says, in my array, put the value I'm giving you at the end of the array. Well, I should say at the end of the values that we've got. So if this is my array, and I've got 3 here and 1 here, and I want to put another value in, I want to append the value, it will go right here. okay, even if my array is longer, like the actual memory allocated. Okay? Insert does kind of the opposite. It inserts it at the beginning. And the way I've actually written the program, it's not very clever. It actually puts it needs to insert it here. And instead of doing something clever like saying 3 goes over here and then put it there, I actually go to here and move 2 into this one, and then 1 into this one, and then 3 into here, and then I put that there. Now, because we don't care about the order of this, that's actually fine. But later, if we want to have an ordered array, we're going to need to keep things in the order that they are. We can't just do this, this efficient moving of things. But as I said, I'm not even going to use insert in this demo. And then erase says erase the value at some point. So it's going to, if I want to erase the value at location 1, which happens to be this location, this is 0, this is 1, I will say erase at 1, and it will go here. That's kind of a bad example because this is a 1. Let's say that was a 7. If I say erase at 1, it will still go to position 1, erase that, and then move everything else back. Okay, that's what it's going to do. And by the way, notice what the type is that I give to the value, the value here for insert and, for insert, values are value types. Don't worry about this. That's called a reference variable. It just means that you can actually look at the actual variable itself. It's not that important right now. And this is erase at the index, which is your size t type, because you need to be able to reference anywhere in that array. Okay? Again, details that you should probably understand, but if you don't get it right now, that's all right. OK, and then finally, I've got a couple more member functions. There is a size function, which just tells you how many items are in. The size of this array right here would be 3, because it's 1, 2, 3. Even though there's extra spots, there might be extra spots, the size is 3. OK, and then value at, if I want the value at 1, it gives me 7. OK, and then finally, I've got, and by the way, if you're looking for a value and the size is less than that value that you're looking at, it's going to fail. Because let's say I want the value at 4. 0, 1, 2, 3, 4. Well, there's nothing there, so it should fail. Okay? So that's my assertion there. And then finally, average height is the little function I'm going to write to actually compute the averages. Easy. Questions on the H file? OK. All right. Let's look at the CPP file. Let's see what I actually wrote in CPP side of things. Let's see, there's a bunch of boilerplate stuff up here, some includes, some other stuff. I redefined my capacity. You have to do that in C++ in your CPP file and in your header file, unfortunately. And here's my constructor. It's the easiest constructor you'll probably ever write. It just sets the used, which is the amount of data, to 0. Okay, it's rather how many there to 0. Why 0? Because that's what I started with. I start with a nice empty array. Okay, start with an empty array. And that's that. OK, let's look at the append function here. The append has one of these assertions in it. It says, is the size less than the capacity? And by the way, size gives you used. OK, we'll get to that in a minute. So at the beginning, let's say, I didn't even show you what the capacity was. I don't know where that was. Maybe I missed it in the H file. The initial capacity of this array is going to be 5. OK, it's going to be 1, 2, 3, 4, 5. OK. So you've got the append value does this. It takes the value. It makes sure that it can fit in our array. And then it says, take the value that used is and put our value that we've asked for into that position. How does that work? The compiler starts out and size is 0, right? You append a value. You say, here, put value 7 into my array. And it says, OK, first is the size less than the capacity. Well, capacity in this case would be 4. Let's make it 5 like we're going to make it in anything. Capacity is 5 spots, and the size is 0. Well, where can I put the first value? At 0, right? So I put the 7 right there. And then I increment how many we have, because I've just added 1. So I add 1 to the used. And so now used is going to be 1. And we've now got one thing in our array. Okay? So it's a nice way to use that value to figure out where to put the value. Use the used amount, how many are in our array, to put that value in. OK, don't worry about insert. Insert basically is just a loop that starts at the end and moves everything over. Not very efficient. OK, and then size. Size just returns the variable used. Why do we do it this way? Again, it's data hiding. It's so that anybody else using your program can't go and change the used variable. Why do we do that? It has to do with the fact that we want to have kind of control over what we write. Question?
So you defined used.
I did, yeah. In fact, I thought I did it in the H file. I don't know why I didn't see it. Maybe I glossed over. But yes, we defined used as a size t. No, sorry. Yes, a size t integer. We said how many it's going to. That just holds the number of elements. I defined that. OK? All right. OK, let's see. And then value at just returns the data from our array at the index we asked for. That's all it does. And then, finally, the heights function is relatively simple. First of all, it says, is my size greater than 0? You can't have an average for 0 values. It doesn't make any sense. You end up dividing by 0. So you might as well assert that it's greater than 0. And then it says, OK, I'm going to start my sum out. I'm going to do this loop that adds up all the values into the sum. And then I'm going to return the value of the sum divided by the size of the array, which is the average. OK? Makes sense? Yes, question?
What is it like specifically about like the way that you did the type def, so that now you have to refer to it with the like double colon operator?
In the previous function, let me see.
Like height value type instead of just like value.
Oh, yeah. Because value type is inside the height definition file, like it happens to be inside the definition of the class. You have to make sure that you refer to it there. If you were outside this class, value type doesn't mean anything.
Okay.
So somebody else could use a different value type outside of your class. Good question. OK, so now we've seen what this thing actually does. I won't bore you with the tester function, except to say that it runs this little function that asks for heights. Let's see, make. OK, it's up to date. And then heights tester. And there we go. And it says enter celebrity heights. OK, so I have this list of celebrity heights here. Let's see, am I here? Yeah. I have this list of celebrity heights called celebrity heights. And I will look through it. So somebody give me the name of a celebrity. Gary Coleman. OK, let's see if we can do this. See, so I'm going to use a function or a program called grep, which searches through files. Coleman, I think, for Gary Coleman. All right, and then I want to look through celebrityheights.txt, and there's a whole bunch, and there's Gary Coleman. Gary Coleman happens to be 55 inches tall, 4 feet 7. Not a giant man. OK, well, he was. Not with us anymore, sadly. OK, so we are going to put 55 in for Gary Coleman. OK, another celebrity.
Peter Dinklage.
Who?
Peter Dinklage.
How do you spell that?
Dinklage.
I'm just going to do Dinkle. OK, Dinkle, celebrity heights. Let's see. There it is. Look at that. There he is. OK, that's the one you're looking for, right?
Yeah.
Another relatively small person. 53. OK, 53 inches. OK, give me one more. Somebody a little taller. Sorry, Shaq? OK, Shaquille O'Neal, right? Let's see. Let's do this. Let's see. SHAQ, I believe. There we go. He happens to be 85 inches tall. OK. I told you this list has a lot of people in it. 85 inches tall. OK. So now if I do another return, it will actually check them. So we have 3 celebrities in our list. And the average height is 64.3 inches. OK. All right, so let's say I want to run this again. I want to use some other heights. So let's say 65 and 62 and 64 and 50 and 43 and 61, and we failed. OK? Our assertion failed because the size is less than capacity. What do we do?
Make capacity larger.
Make capacity larger? Sure. So what we could do is we could go back into our header file, we could find the capacity line, and we could make it like 10,000. Let's say, well, we never think we'll have more than 10,000 celebrities, right? And we could do that. And then we'd have to recompile, and then we could rerun the program. But I have a question for you. How many times do you have to, when you're using Microsoft Word, does Microsoft Word crash with some assertion, and you have to go in, find the Microsoft Word source code, change some value in it because you want a really big file, right? And then go recompile Microsoft Word and then start it up again, right? That never happens, right? For obvious reasons, because just increasing the capacity is not really the best way to do this. Okay? There are other methods that are better. Now you could say, well, look, I know I'm never going to have more than 10,000 celebrities in this list. But I bet 10 years from now, if celebrities.com or whatever, still celebrityheights.com still exists, it's probably going to have more than 10,000 in there, right? Like 100 years from now, it's going to have a lot of other heights in there. And so you can't really guess, and you shouldn't try to guess the maximum size of your data structure. So therefore, we kind of scrap this method in the sense that we say, all right, let's try something a little bit different. Let's try doing a dynamic solution. Okay? So let's see what the dynamic solution looks like. See what we've got here. Okay, this is the .h file again. Okay, and I'll explain what the dynamic solution means in a few minutes. Same thing, type def. We're going to do that. Don't worry about the words underneath there. Now instead of capacity, I've got the default capacity. Okay, because you might as well make it, but you're going to have to start with something. You might as well pick something. You can pick any value you want. In fact, we're going to allow the person who runs your function to pick that capacity if he or she desires. Okay. Whoops. Oh no, what did I do? Went to the bottom today. Oh no. There we go. Okay. Where were we here? There's your constructor with our default capacity now, our initial capacity. And then we're going to have some member functions. Nothing's going to change about the definition of append or insert. That's nice. It's a very object-oriented solution in that we don't have to change anything about the definitions. Okay. And then nothing changes there. We do have this other function called reserve. Now here's what reserve does. Okay. In our array, we have, it starts out like this. Okay, it starts out with some number of values. Okay, this is kind of like a train car, right? Where you've got a certain number of train, where you've got a certain number of cars in your train, and let's say the whole train is filled up, and you get to some other station, and nobody wants to get off, and people want to get on. So you say, well, all right, give me another train car. Okay, and you get another train car. The problem is it's actually a little more difficult than that. It's not that they just you add another train car. It's that you say, give me a whole nother train that's actually one longer than the one that we had before. So 4 and 1 longer. Okay? And this is what the reserve function is going to do. It's going to ask the operating system for more memory that's long enough to hold what you've asked for. Okay, so it's dynamic in the sense that you get to ask for that extra memory. Okay, and what's going to happen is it's going to give you this piece. Unfortunately, the operating system can't say, oh, you want one more piece? Here, have another little piece off here. Leave everything and just get that other little piece. It can't do that. Okay, there's lots of reasons why it can't do that, because it would have had to know you were going to ask for it, because otherwise it should be able to give anybody this piece. Right? So but it says, all right, look, I'll look through memory, I'll find a piece that's long enough for you, and I'll give that to you. Okay? And then what you've got is you've got this array here that has all these variables in it. You get a whole new train, and you have to actually move the numbers into the new one, get rid of the old one, and then go on your business with extra space. Okay? That's what reserve is going to do for you. Okay? And we'll see how that actually manifests itself in the code. Okay, let's see, anything else change? Size, nope. Value at, nope. Average height, nope. Okay, I think that's about it. Oh, here we go. I didn't even show you this before. This is actually the definitions of these things. Here's where I define the default capacity to be 5. Okay, what else did we miss here? I think we missed the destructor, didn't we? Did I put that up here? I didn't actually put that up here. The one thing that you're going to need in this is not just a constructor, but you also need this thing called a destructor. If you ask the operating system for extra memory, you need to tell the operating system when you're not using it anymore. Okay? At the end of your program, the operating system gets back all the memory it gave you. But in the meantime, if you do this thing where you move information from this array into this array, well, guess what? You need to delete this array and tell the operating system that you've done that. Okay? When your class gets destroyed, that's the function of the destructor. Destructors are actually really pretty easy. But they just tell you, look, we're done using the data that we asked for. OK. All right, so that is, and here's where we did this before. Before I had value type data, and I actually defined how much data it was, the capacity of it. Now I'm just using this, what we call a pointer, which tells me this is going to be an array. I don't know where it is yet. I don't know what it points to yet, but it's going to be an array of values. And the operating system will give me that. OK. And we've got our used, which tells how many, and our capacity, which actually tells how big the current piece of data is that we are using. OK, questions on that? Yes?
Would you normally suggest when you're declaring like a constant variable to put it in public versus like making it a private number?
Question is, if you're making a constant variable, would you make it public or private? I don't think it really matters depending on what you're using it for. Yeah, if it's constant, you're not going to be able to change it anyway, so it really doesn't matter. You can still look at it, but you're not going to be able to change it, so it really doesn't matter. But good question. Yeah, I wouldn't worry about doing it either. I mean, whichever one is fine with me. OK, let's look at the CPP file. OK, more boilerplate stuff. Here is our constructor. Now, pay no attention to this one. Pay no attention to the man behind the curtain, right? This is the one we're going to look at. Our constructor is, it just says, give me an initial capacity. OK? And I think I should have put it equals to initial capacity. I think I forgot to do that. But anyway, what it does is it says, I'm going to define what that array points to by using this new keyword and asking for an array of this value. OK? The new keyword says, hey, operating system, give me an array that's this big. OK? And the operating system goes off and does it. Okay? And then it's going to set the capacity equal to this initial capacity. And it's going to say, hey, there's nothing in the array yet. Okay? The copy constructor, we are not going to spend time on this today. But what this is it's a way to make two variables equal to each other. So, actually, if you were going to create a new variable from another one, a new class from another one, you've got to copy that information. And the copying of the information doesn't happen automatically like it would with regular variables. So we've got to go over that at some point, but not right now. Our destructor, very easy. It just says delete our data. And this little bracket symbol means delete the array that's data. Okay? That's all the destructor does. It says when the class goes away, delete the data we're using because we don't need it anymore, and we asked for it. Okay. All right, let's see what else we've done here. OK, append. So we have to change the append a little bit. Because before, append just said, is our array, is the size as big as our array? If it is, we're done. Assert, we got to end. Now it's just saying, now it's saying, if our array is completely full, if used equals the capacity, reserve the amount that we have plus one little extra. Ask for a new train car with one extra car. OK? All right. And insert does the same thing. Let's see. Don't worry about this. It's another thing. It's called the equals operator. If you're saying class A equals class B, you have to put that. Don't worry about it for now. And let's see. That's all the thing you don't have to worry about. And then reserve. Here's what our reserve does. Our reserve says, OK, give me a pointer to a larger array. It's not actually larger yet. It just doesn't point to anything right now. And it says, first of all, it says, if we're asking for the same amount of space, don't do anything. We've already got it. Why would you do that? Well, you might. So you have to take into account doing that. The other thing, the next one says, if our capacity is less than what we've already got, well, don't say take off the last train car. Don't say you're going away. Just make the size equal to the maximum size. That's all. That's all that's really doing. OK? And that's saying our capacity is now the maximum that we have asked for, or that we actually have in the array. And then finally, this is the part that is the big difference here. let me get this up here. It says, now we know we've got it. We're asking for more in our array than we already have, capacity that we already have. So it says, give me a larger array that's the size of the new capacity. And then copy all the data. You could have written a loop. I could have written a loop that loops through the old array and copies the values individually. That's what this copy function does for me. It says, where's the beginning of the array that I want to copy? Where's the end of it? Data plus the amount that we've used. Copy that to the new array. That's all that does. And then it says, delete the old one, because we've now copied the data into our new array, and we're done with it. Delete it. And then it says, set our data equal to the larger array. We didn't actually delete the variable. We just deleted we deleted the memory associated with it. And then finally, set the capacity equal to that new capacity. Okay? The rest is the same. So we don't have to actually change anything else. The rest is all the same. Okay? Let's see how it works. OK. Heights dynamic tester. What I'm going to do, instead of typing in thousands of celebrity data points, celebrity heights, I'm going to actually use another command, another piping command, to pipe the data that I'm using into the file as if I typed it in. I've got a list of all the heights. Okay, so it's celebrity heights only, and it's going to pipe it in just as if it were there, as if I typed it in. So that was pretty fast. Now, there are 6,599 celebrities in the list, and the average height is 68.14. OK, so far so good, right? This actually worked, and it allowed us to make this bigger and bigger and bigger. OK, are there any obvious, do you guys see any obvious things wrong with the program? I don't expect you to, but did anybody notice anything? Yes?
We're only making it bigger by one tram card each time.
Ah.
A little redundant in that essence.
That's a good point. We're only doing it by one. I wouldn't necessarily call it redundant, but we are doing it probably more often than we necessarily have to. Yeah. Did you have another comment?
You might run your infinite loop because you might start building the things forever and ever if there's some bugs.
You might want to build what kind of loop?
You might run into a problem where it just will run infinitely.
Oh, you might. Yeah, it might run infinitely long if you make some mistake or whatever. Yeah, that's what the Control-C button's for, right? So, I mean, in our case, we just get out of it by typing Control-C. What I've done actually, let me clear the screen here. What I've done is I actually have a file called test data 100,000. And what I did was I populated it with random numbers that were like heights. They were in the kind of heights range. Okay? And I made 100,000 of them. Okay? Watch what happens when I run our tester with test data 100,000. Okay. It says enter celebrity heights. Well, what it's actually doing, it's actually processing it. It says that, but it's actually in the middle of processing it, and now it's done. Okay. 67.4604 happens to be the ones for the data I entered. You notice that took a little bit of time, right? It all comes back in this case to time. Is there a way to time that to actually figure out how much it is? Absolutely. We can use a function called time in UNIX, right? And we do the same thing, heights dynamic tester, and let's see, celebrity heights. OK, if we do that, whoops. Oh, sorry, not the celebrity heights. I want the big one. The celebrity heights was really fast. Test data 100,000. There we go. OK. Test data 100,000, and it's cranking away, cranking away, cranking away. And after 6.4 seconds, it tells us it took 6.4 seconds of real time. In other words, that's how much you had to wait. That's how much you guys had to, we had to sit here and wait. 6.4 seconds. The user time was the amount of time it took to actually do stuff like copy the data in here. And then the system time was the amount of time it actually took to ask the memory system to give us all this other piece of memory. OK, so what it did was it said, and like you were saying, what's your name? Dylan. What Dylan was saying was, hey, it's asking for one little tram car at a time. Think about it this way. If we put celebrities into our car, and every stop, they all had to get off, they had to get a new train, bring a new train in, everybody had to get off, get on the other train, they'd riot, right? Because it would be like, that's not, celebrities aren't fit for that, right? You have to, you don't want to be quite that obtuse about when you're designing it. Okay? So we've kind of figured out where one of our bottlenecks are. And when you're designing your own programs, you want to figure out where these sorts of bottlenecks are. So what can we do? Can we change that value? Yes, question.
Instead of adding one each time you reach the capacity, you can multiply it by 2.
Instead of adding 1 each time, you could multiply it by 2. Sure, let's do something a little less tricky than multiplying by 2. That's a good answer. Let's just add 2 each time. Right? Let's see what the difference is. Let's just, I like your answer, but let's look at doing it. So let's see, .cpp. Instead of, this is in the append, I believe is where we were doing that. OK, here we go. Instead of adding 1, let's just add 2 and see what that does for us. Make, and then run it again, and we'll see what happens. Now we're adding 2 each time instead of 3. Oh, look at that. It went from 6.3 down to 3.8 seconds. Okay, why did that help? Because we actually gave ourselves a little extra buffer room. So every time we added a new value, we didn't have to ask for new space. We just had to do it every other time. Okay, not so great, but let's do your example. What's your name?
Yuval.
Yuval. Yuval says, you're crazy. Don't do it just by 2. Do it by multiplied by 2. OK, so did I miss it here? Hang on. Nope, there it is. All right, so this time we said used plus 2. Instead of used plus 2, let's now every time ask for twice as much as we've already have. OK, and let's make it, and let's run it. I'll just do it up here. OK, boom. 0.038 seconds. OK? That was a phenomenal increase. In fact, this is probably the best increase you'll get on any of your code all year, right? By doing like that much, right? That's like, let's see, it was 6, 10%, or let's see. 1/10 would be 0.6, 1/100th, so 2 100ths. Yeah, 2 100ths? No, 1 200ths. Whatever. It's much, 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 much faster by doing that. OK, is there a trade-off to doing that? Question, comment, yes? Yeah, that's exactly right. You are wasting memory by doing that. In some sense, you're wasting memory in that you've had now. For what it's worth, you've got a pattern of doing this. So the first time you're going to have 5, if we started out with 5, and then you're going to have 10, and then you're going to have 20, and then you're going to have 400, and then et cetera, et cetera. Each time, sorry, what am I doing? How about I'm thinking squaring. No, you're multiplying by 2. So first you're going to have 5, then 10, then 20, then 40, right? And you're going to do that, but you do have a pattern. But you're right. If the last one that you asked for was just 1 and then you're done with your program, you've got basically half the space wasted because you're not using it. So that is the trade-off. Okay? A lot of programming languages do, though, use something like this in their dynamic array implementations. What they do is they've kind of figured it out. They've done lots of tests on usage cases, and around 2, 1.9 to 2 is about what they do when they need more space in general. Okay. So anyway, I just wanted to show you that. One of the things that we're going to start thinking about in this class is efficiency. I mentioned it on day 1. I'm mentioning it today. I'll probably mention it every day of the class. How to make your programs more efficient and how to avoid doing things like copying things multiple times. It's about a few things. It's about looking for bottlenecks in your code, looking for where you've done something that's easy and obvious, and trying to be a little more clever. You don't want to be too clever. But you want to be clever enough that you avoid the 6-second run times so that you can get down to the 0.1 second run times or whatever. Okay? All right. So that's all I got for today. Any questions on the class, the assignment, what we went over? Yes?
Wondering what the general homework cycle is? Is it you do 1 project per week or?
It's probably going to be, I think there's going to be a total of 6 or 7 total homework assignments. But some of them will be multiple weeks long because they're going to be rather large programs. So not every week. I think 2 weeks is probably going to be the next one. Yeah. But we'll get the assignment next week at the very least. Okay. Anything else? Yes?
Will you put this code online?
The code is already online. So you can it's in a zip file, a couple of zip files. All right. We'll see you guys Monday.
When I ran the tester, it said my